All right, so now we're going to get into Module 5, not 3, Microfluidics, laminar flow, and mixers. So now we're going to actually get into some of the specifics of how fluid flows through a microchannel and some of the technologies that people have used for doing various types of fluid, for doing various types of diagnostics in microfluidic devices. This module, this part of the microfluidics module is going to cover laminar flows and mixers. And after this, we're going to talk about various ways that you can control fluids in a microchannel. So we'll talk about pumps and valves and other types of integrated devices on the chip that allows you to manipulate flow. This one is just the basics of flow and a little bit about how you can mix flow. The third part of the microfluidics module is going to talk about separations. So how can you separate molecules in flow? How can you separate different particles by their size or by their other properties? Okay, so there's going to be quite a bit that we're going to be doing in the microfluidics module. So I've sort of split it up into three sub-areas. So in this module, we're going to start by talking about basic concepts of shear stress, Navier Stokes equations, the properties of fluids. We'll also talk about chemical diffusion. So these are all just a little bit of a background for those of you who have a chemical engineering background or fluids background, mechanical engineering background. This will be very familiar to you, but it's really all to get us all on the same page here. The next part we'll talk about laminar flow. Okay, for the early part of microfluidics from the 90s, a lot of the interest was in laminar flow. The fact that two streams, if you combine two streams of fluid together, the two streams will flow parallel to one another. So we'll talk about some of the science and applications of laminar flow. Within that, we'll talk about the Reynolds number, which we've already mentioned, the Peclet number, the diffusion length, should be PE. Then we'll talk about gradient generators. Gradient generators are microfluidic devices which can generate very specific concentration profiles in the solution. So you could have a high concentration of a chemical here, a lower concentration here. You can create a gradient between them. You could create a very sharp concentration profile, a step profile in concentration. You can create linear, exponential profiles, and so on. And then we'll talk about microfluidic mixing mechanisms. So how can you actively and passively mix fluids at the microscale? Let me just adjust this. So one of the things about microfluidics, because you have laminar flows, you have the absence of turbulence. And in turbulent flow, the fluid like sort of rolls and folds into each other, sometimes in unpredictable patterns. Turns out that's very good for mixing. But in microfluidics, you have laminar flow, streams running parallel to one another. This is not very good for mixing. If you want to mix, you want the fluids to be like turning and folding upon each other. You want the fluids to be mixed. So there's ways that you can enhance that rotational motion of the fluid to encourage mixing. Okay, so this will give us sort of a background and a foundation for the other areas of the microfluidics that we'll talk about in the future modules. Specifically, the separations module, where we talk about the behavior of particles in flow, the behavior of cells in flow. This slide is a review of stress and strain in mechanics, just so we're all on the same page. This is from Steven Centuria's book, Microsystems Design. It's a MEMS book. If we consider this cube, okay, some of you have seen this thing many times before in like mechanics textbooks. But in mechanics, they consider a mechanical element. Okay, and mechanics are always concerned about the forces on that element. So since we're talking about fluids, consider this block just a small cube of fluid. okay, that may be flowing through a microchannel and may be stagnant, whatever. It's a small packet of fluid. Now, on that packet of fluid, there are many forces being exerted on it. Some of these forces are normal. Okay, a normal force would be a force that's orthogonal to the surface. So that's given by sigma y, sigma z, sigma x. Okay, the normal forces would cause the object to, compress or decompress. Right? If it got squashed in one direction, for example, or if it was getting decompressed in one direction. For example, here, what we're doing here is it's being compressed in the y direction, but as it's being compressed in the y direction, it expands in the other direction. Right? If you squash it one way, it expands the other way, right? So we'll get to that Poisson's ratio in just a second. But basically, normal forces can cause, or what's called axial stress, can cause this element to deform. You can basically squash it in one direction or the other. The normal force can also push that element along. Right? In the case of fluid, the pressure from one side of the channel is pushing the fluid packet in one direction. So that's a normal force. By the way, the normal force is also denoted tau zz, tau yy, and tau xx. All right, the units for all of these forces are newtons per meter squared. All right, so you can think about it as a pressure. The pressure has the units newtons per meter squared. There's also shear forces acting on the element. Okay, shear forces act to deform the cube. So the shear forces here would be tau zx, tau zy, tau xz, tau xy, and so on. Now, shear force is a force that is tangential to the surface. Okay, so if you imagine taking this cube and shearing it, meaning like just pressing on it and then running your hands like tangential to the surface, then you're going to cause it to deform in a different way. Right? You're going to cause it to, a square shape would become sort of like a rhombus shape like this. Right? So it's a different way of deforming the element. So these are the two ways that you can deform the element. This is what's called a axial strain, normal strain, and then B here is an example of shear strain. Both of these things work to deform the element in certain ways. So if we're looking at the deformation of a beam, it's based on this type of mechanics. If we're looking at the forces that affect the movement of a fluid, then we look at these equations. Okay, this is just from the very basic concepts. The concept of stress and strain, we can just cover this real quick. Strain is given by epsilon, so the strain is the change in the length of the object, the change in this dimension, divided by delta x, divided by the size of the object here. Okay, and so you can have a similar definition for the strain of the object. These can also all be defined as differential equations. So the forces on this cube can be expressed in matrix form through a force tensor, and noting a certain symmetry. Tau xy is equal to tau yx, and tau xz is equal to tau zx. This is due to symmetry, and tau yz is equal to tau zy. Basically, like the two shear force vectors here on a specific surface are equal to one another. And if you want to find the force on the element in a specific direction, and that direction is given by this vector n, you take the dot product of that vector n with this force tensor. Okay, so this tensor is a compact way of representing all the forces that are acting on the fluid element. Okay, and if you happen to be interested in the force just in a certain direction, you can dot this tensor with the direction of the force that you're interested in finding. So I mentioned stress and strain. Okay, there's a normal strain and shear strain. There's also, remember, there's a concept called the Young's modulus. This applies to solid materials. This is not necessarily the case with liquids. The stress, the normal stress is equal to the Young's modulus times the strain. This isn't the case of an elastic solid material. Fluids behave differently, of course. And then just recall there's something called the Poisson's ratio. The Poisson's ratio describes like if you were to stretch out an element in one direction, it compresses in the other direction. So if you were to stretch this element out in the x direction, it compresses in the y direction. So these were the the ratio of the two is given by this linear constant, which is Poisson's ratio, typically between 0 and 0.5. So just a little bit of stress and strain mechanics to remind you all of what that was. Now, in the case of fluids, we can look at this cube as a cube of fluid. All right, and that cube of fluid will have a force tensor on it. Now, remember tau xx, tau yy, and tau zz. These are all the normal forces acting on the fluid, and these are some of the shear stresses acting on the fluid. Okay. For a Newtonian fluid, these are what each one of these forces comes out to. These are the normal stresses, 2 mu dux dx. We'll talk about viscosity in the next slide here. And then this is the stress, the normal stress in the y direction. This is the normal stress in the z direction. And these are all the shear stresses. Okay. Notice they all have to do with something called the viscosity. The viscosity represents sort of like the thickness of the fluid. A very thick fluid will have a high viscosity, and that will have more shear forces exerted on it. Okay. Now, just an intuition behind where, the intuition behind stress. We'll talk about this in just a second. Actually, maybe let's talk about this, and we'll come back to the previous slide here. Whenever fluid is moving through a channel, there creates a velocity gradient. The reason why a velocity gradient is created is because at the walls of the channel, the fluid doesn't move. The velocity of the fluid is 0 at the walls of the channel. This is the case at the macro scale. It's also the case at the micro scale. Velocity of the channel wall, we say it has a no-slip boundary condition. If that's the case, then the velocity is 0 there. So let's say this x-axis represents y equals 0, represents the wall. Okay. The fluid velocity there is 0. These arrows are showing the fluid velocity. Velocity here is 0, and as we go away from the channel, the velocity increases like this. So this creates a velocity gradient. We talked a little bit about this in the first lecture. This gradient is given by du dy. U is the velocity, and y is this y coordinate. Okay, so the slope of this line is the velocity gradient. Okay, so what a velocity gradient is, it means that some fluids are, the fluid here, for example, is moving faster than the fluid here, right? So if you imagine we have like flow in a pipe, there's, if we imagine a block of fluid, let me just draw this. Alright, it's not liking that. Fine. Oh boy. Okay, it looks like PowerPoint has decided to stop working. So let me just shut this down. Restart it. Okay. So imagine that we have like a block of fluid here. So that cube is sitting right here. So the top of the cube is going to be moving at a faster velocity than the bottom of the cube, right? So that's creating that shear stress, that sort of like, that rubbing motion. Velocity on the top is faster than the velocity at the bottom. So that fluid element will, experiencing shear stress. So that is the origin of the shear stress that you see here. Whenever you have a velocity gradient, fluids moving at different velocities that are sitting next to each other, you create a shear stress. Okay, two fluid layers rubbing up against each other because they're moving at a different velocity. So the friction inherently results in a power dissipation in the fluid. That's called, shear dissipation, or it generates. Actually, it represents a power loss in the fluid. So the shear stress, there's a simple formula for it. Tau is equal to mu times du dy. Mu is the viscosity of the liquid, and you can see some examples of various viscosities here. Water has a viscosity of 0.01. This is using the units poise. These are not necessarily the MKS units here, but the viscosity of water, it just compares to the other viscosities that we have. Acetone has a smaller viscosity than water. You can see that whole blood has viscosity quite larger than water, and something like glycerin or oil has much larger viscosity than water. Okay, so the thicker a fluid is, the higher this viscosity will be, and the larger the shear stress will be. The units for shear stress is newtons per meter squared. So the power dissipation, P, is equal to the shear stress times du dy. Okay, and the shear stress here is given by u times du dy. So the second derivative of the velocity will give you the power dissipation in the fluid. Newtonian versus non-Newtonian fluids. A Newtonian fluid, the viscosity is constant. Okay, so something like water would be the example of a Newtonian fluid. The viscosity is constant. Non-Newtonian fluids, typically things where we have a suspension of some particulates within the fluid. For example, blood. It's not just liquid, it's made up of red blood cells, made up of platelets, all sorts of stuff in the blood. That's considered a non-Newtonian fluid. This chart is giving you sort of a relative idea of what the viscosity is, but in a non-Newtonian fluid, the viscosity is actually a function of shear stress on the fluid. Okay. So depending on how fast blood is moving through a channel, its viscosity will change somewhat. Okay, the viscosity depends on the shear rate. Okay, a shear rate, by the way, is the same thing as this velocity gradient. It has the units 1/second. Another thing here, you can notice the gases here, they have a much smaller viscosity than water does, but it's not zero. Okay, as long as you have molecules and there's some friction between the molecules, there will be some viscosity. The only way you can avoid viscosity completely is if you have vacuum. So, getting back to this slide then. So we talked a little bit about viscosity. So viscosity creates shear stress. And so you can see that this shear stress is appearing in these terms here. Okay, they have to do with the velocity gradients in the y direction and the x direction and the z direction. So if you simplify the force tensor in a specific case where you have rectilinear flow along the x-axis. So why are we selecting rectilinear flow along the x-axis? Because we have a rectangular cross-section microfluidic channel. In most cases, that's the type of flow you're dealing with. All right, so how does this simplify then? The velocity in the y direction is going to be 0. By the way, this is the these are the vectors here. Okay, the channel is in this direction, so the flow is going in the x direction. Okay, the y is the height of the channel, and z is across the width of the channel. So obviously, the velocity in the y direction, if you just have flow going this way through the channel, velocity in the y direction, velocity in the z direction is going to be 0, and all their respective derivatives are also going to be 0. All right, so this then simplifies to a large extent. You're just left with 4 terms left in the force tensor. Okay, this is the general formula. If you, for example, if you just want to find the force acting on the bottom surface of the channel, then you can just input the direction vector n. So 0, 1, 0. 0, 1, 0 will give you the normal vector in the y direction, and that will give, if you multiply this out with the matrix, you'll get just this as the, this would be the force vector. So this would be the shear stress on the bottom surface of the channel. Okay. So this is an example of one simplification. I mean, obviously, if you have a different cross-section channel, if you have a circular or triangular cross-section, then your uy and your uz will still become 0. You'll still have the simplification. But I just wanted to show you that these equations are the general equations that you could then simplify depending on what type of channel or geometry that you may have. So we talked about shear stress and viscosity. I just want to mention a few things about the properties of fluid. So we talked about shear stress and viscosity. Other properties of fluids that you're already familiar with, the density of the fluid. Okay, when you're dealing with the density of liquids, water, for example, has a density of 1,000 kilograms per meter cubed. When we're dealing with liquid flows through a channel, the density is fixed. Okay, so that's what's referred to as incompressible flow. The density does not change. If you're dealing with gas flow through a microchannel, then you have compressible flow, because gas can be at high density, it can be at a high pressure or low pressure, right? The equations for compressible flow are a little bit more complicated than incompressible flow. So we'll see what the Navier-Stokes equations in a few slides later. But I just want to make sure that we're all on the same page with that. Okay. Liquids, incompressible flow. Gases, compressible flow. So another thing that happens when we're dealing with liquids, specifically when we have a liquid and air interface, or we have multi-phase flow, is this problem of surface tension. Not a problem. It's just a physical phenomenon. It often causes problems if you have air bubbles in your microfluidic device, for example. But it's actually a very powerful force too, which can be used to pump liquids through a channel by capillarity. So surface tension is a phenomena that occurs at the interface of two immiscible liquids, or two immiscible fluids. For example, at the interface between liquid, fluid, and air. Now, water is made up of H2O molecules. We talked about it on the last slide. There's that phenomena of hydrogen bonding that attracts the water molecules to each other. So there are intermolecular forces that attract water molecules to each other. This diagram is just from the hyperphysics. Now, within the water, within the bulk of the water, these intermolecular forces are balanced, meaning that this water molecule is going to be equally attracted to here, as it is to here, as it is to here, as it is to here. All right? So those forces somehow balance one another. But at the surface, if we take this water molecule up here, for example, it's going to experience attractive forces between here, here, and then here, but it doesn't have any water molecules on the upper side because it's at the surface. The fact that these forces then become unbalanced, this creates a tensile stress, a tensile force at the surface, a tension. Okay, you can think about it as, another way of thinking about this is just there's attractive forces between the molecules of water on the surface. Okay, and those, the attractive force there creates some type of tension on the surface of the water. Attractive force. Tension, you can just think about taking a balloon and pulling it apart. That creates tension. So at the microscale, this tension that's on the surface of the water is actually strong enough to hold up things like paper clips, strong enough to hold up an ant. Okay, because at the scale, the gravitational forces are insignificant compared to the surface tension forces. So basically it forms a skin on there. Now if we get into more specifics of it, we can look at the Young-Laplace forces at the interface. And it's given by this equation here. Now the force, let me just describe what this is. FLS stands for the force at the liquid-solid boundary. So that's given by this right here. FSA is the solid air. At the solid air interface there's a force, and at the liquid air interface there's another force. Okay. These are two examples of capillarity. I'll show a little bit more on this slide here. There's something interesting that happens whenever you have a liquid, air, and then a solid, what's called a triple interface. There's two possible ways that this can go about. One is if you have a hydrophilic surface, and one if you have a hydrophobic surface. So let's assume that this is water. Okay. Then if the solid is hydrophilic, then the surface of the water against the surface of the solid, the water will curl up like this. Okay. The way that you can imagine this is that if the surface is hydrophilic, water-loving, the water molecules like being on the surface. So these water molecules will be attracted to the surface, and it'll actually want to go up the wall like this. By contrast, if the surface is hydrophobic, the water molecules will prefer not to be on the surface, so the water molecules will try to get away from there, creating more of a stack of water molecules here. We don't see these effects at the macro scale because the weight of the water is more significant than these surface interactions. I'll get more into that on the next slide. Okay, but at the microscale, if we were able to zoom in on this, we'd be able to see these. We can draw each one of these three forces, and this is really just a geometric problem here. Is that this liquid-solid force and the solid-air force and the liquid-air force is all represented by can all be represented by this simple geometric equation. As part of this equation, there's this theta. This is the contact angle. Okay, this is the angle that forms between the liquid at the liquid-solid-air interface. So it's this angle that you see here. It's the contact angle. We talked about contact angle earlier. So surface tension scales as the length. It's newtons per meter. The weight of the liquid scales as length cubed. Right? So as you go into smaller systems, surface tension can actually become more significant. And in fact, many microscale devices use surface tension for pumping. You can actually use it as capillary pumps, for example, electrowetting. We'll talk about droplets in a second. But if we're talking about capillarity, capillary force, suppose we have a capillary like this, a microchannel, and that microchannel happens to be hydrophilic. The water molecules are going to curl up near the sides of the channel like this because the water molecules they like the walls of the channel. It's hydrophilic. So if you zoom in on one of these forces here, the water molecules are actually exerting a force on this whole volume of fluid here, because the water molecules are trying to try to go to the surface here, and they're pulling other water molecules with it. This tension on the surface of the water, the surface tension, is actually pulling the fluid up when it's a hydrophilic surface. If it's a hydrophobic surface, the opposite happens. Let's look at the case where it's hydrophilic. In the case where it's hydrophilic, actually the water will actually rise in the capillary. You don't have to pump or do anything. Like, the water will rise on its own just through surface tension forces that you can see here. It'll rise to a certain height given by h, and then at some point it will stop. Where it will stop is when the two forces are balanced. So when water is going up the pipe like this water has some weight to it, right? So there's a hydrostatic force. Okay, there's literally the weight of the fluid in here. And that weight of the fluid is going to make this fluid want to come down. But then there's a capillary force. The capillary force is based on surface tension. That's what's pulling the liquid up into the capillary. So when these two forces are balanced, the hydrostatic force is balanced with the capillary force, you can determine the height of, this. That's what determines the height of how much the fluid rises in the capillary. The hydrostatic force is given by rho times g times pi r squared h. So the way that we get the hydrostatic force is just the hydrostatic pressure multiplied by the cross-sectional area of the capillary. But intuitively think about this. If we want to get the weight of the fluid in the cylinder, we just take the density and multiply by the volume. That's weight. Right? So the force is equal to the mass times the acceleration. The mass is pi r squared h, the volume, times the density. So there's your mass, multiplied by the acceleration, gravity. All right, so this is literally the weight of the water in the capillary. The capillary force is given by this equation here, 2 pi r times the surface tension times the cosine of theta. That's the contact angle here. All right, the surface tension is this is the surface tension of the liquid-air interface. All right, so that would be sigma LA. So the higher the surface tension is, or the smaller the contact angle is, the higher this capillary will rise. So it's actually an indirect way of measuring the surface tension of a liquid. So any questions so far? All right. Another phenomena that results from surface tension. There's a lot of physics. Just covering some basic physical concepts for you here in this slide. There's a Laplace pressure inside a droplet. Now, again, think about surface tension as the skin of a balloon. Okay, when you blow up a balloon, there's a tension on the surface of that, on the surface of the balloon, right? That membrane is under tension. Now, another thing you notice is that the pressure inside of the balloon is different than the pressure outside of the balloon. Which side has a higher pressure? Inside. Yeah, inside of the balloon has a higher pressure. Why? Because you think about the skin of the balloon. The skin of the balloon is under tension, right? So that the skin of the balloon is it's pushing the air molecules closer together inside the balloon. So the balloon has a higher pressure than the outside. The similar concept applies in the case of microdroplets. When you're at the smaller domain where surface tension is starting to play a big role. So surface tension scales as length. I mentioned that. So the pressure difference between the inside and the outside of a droplet is given by this Young Laplace equation, which basically says that the PD, the pressure inside the droplet minus the pressure outside, is equal to 2 times the interfacial tension. Interfacial tension would be has to do with the surface tension between this phase and this phase. So if you're just talking about a droplet inside air, then it's just the same thing as this, the liquid air interfacial tension. But if you're talking about a droplet in oil, then there's a different interfacial tension for water in oil. So this is the interfacial tension, and then this is the R, so the radius of the drop. So notice that the pressure difference between the inside and outside of the droplet goes as the 1 of R. So when you get to small r, the pressure difference goes way up. It can be up to more than 1 atmosphere. So for this reason, if you're trying to make small drops tend to be unstable unless you have a way to reduce the interfacial tension here. If some of the concepts were not as clear from the previous slide, this is another nice set of diagrams from Ellis Meng's textbook, Biomedical Microsystems, which just talks about contact angle and capillary force. At this point, they're concepts we've described already. Contact angle we talked about earlier. The contact angle is defined as the angle that forms between a liquid, solid, and the gas. And you can see that this angle is right here. As I mentioned, there's the properties that you're concerned with here. The surface tension of the solid-liquid boundary, there's a surface tension of the liquid-gas boundary, and there's a surface tension of the solid-gas boundary. Okay, those give you the equation for the contact angle. Okay, because these represent the 3 different types of forces at work here at this triple interface. Hydrophilic surface will have a contact angle less than 90 degrees. A hydrophobic surface will have a contact angle greater than 90 degrees. If you have a hydrophilic surface and the liquid happens to be water, then the curvature of the interface of the capillary will look something like this, and the water will rise inside the capillary. This is what we saw on the previous slide. And then this diagram also shows if you have a hydrophobic surface, the opposite effect will happen. You could dip the capillary into a liquid, and it will actually try to resist the uptake of liquid into the capillary. And you'll have the exact opposite situation here. In both cases, you have the same formula that applies. It's just an inverse problem here. Okay, so this goes to show you. Notice that these heights here, the h, it has to do with a at the bottom. Okay, a in this case is just is the radius of the capillary. So as the radius of the capillary goes down, these lengths go way up. Right. So it's interesting that you could actually pull. If you have a very thin capillary, the entire capillary could fill completely just by capillarity. Right? Again, you have this A at the bottom here. The smaller your capillary is, the larger the height. You could fill the entire length of a capillary if you wanted to, just by this capillary motion. And in fact, a lot of microfluidic devices, some of the point-of-care diagnostics or the passive devices, where you don't want an external pump. You have a lot of microfluidic devices that just fill themselves by capillarity.
That's hydrophilic,
yes.
Right? So
this is if you have a hydrophilic channel, right?
The hydrophobic would actually not fill?
Yeah, hydrophobic will do exactly the opposite. So this can be a problem too. I'm glad you brought that up, Jeremy, because if you have a hydrophobic channel, the channel will actually resist you putting liquids into the channel. Okay, and in which case you just need a pressure pump to drive fluid into the channel.
So could that actually cause pressure in that? So if you insert a capillary and you create pressure in that volume too, right?
If you insert a capillary into
There's a hydrophobic capillary, inserting it into that volume.
Into a volume of fluid like this?
You'd be creating pressure because you're displacing.
Well, so in this case, are you talking about this situation here? So you're dipping a hydrophobic capillary into like a pool of liquid, right? So there's two things that work here. It's the exact inverse of this problem. You have the hydrostatic pressure would try to drive this liquid up into the capillary. Hydrostatic pressure is just the fact that you've dipped a capillary down into the depths of a liquid. Just like if you took a straw and you put it to the bottom of the ocean, there's so much pressure at the ocean it would just come right out. But you have this capillarity issue too. The capillarity is preventing it from happening. So in that sense, you're just like here you have a hydrostatic pressure that's trying to bring the fluid down. Here you have a hydrostatic pressure that's trying to drive the fluid up. So it's interesting. But these are things that you actually have to be careful about. The surface properties, tying this back to last module, the surface properties of your channel are in fact quite important in microfluidic devices because you have capillary forces at work. This slide is just to show you the viscosity and surface tension values of common liquids. For water, you can see that the surface tension changes from 75 millinewtons per meter at 0 Celsius down to something like 58 at 100 Celsius. So it's quite sensitive to temperature. I guess what happens is that the intermolecular forces between the molecules they decrease at higher temperatures because the molecules are vibrating more. Let's see. NaCl, I think this has a relatively high surface tension as well, likely due to the ionic interactions. Hydrophobic liquids like ethanol, they have less intermolecular forces, so they have a lower surface tension. You can see that things like hexane is just a hydrocarbon chain. It's a very non-polar molecule, so that has low intermolecular forces, and it has very low surface tension. Material with very high surface tension is mercury, but it's also quite toxic. So these are just some properties of common liquids that are used. So getting to the Navier-Stokes equations then for single-phase microfluidics. So we're talking about the flow of a single liquid through a microchannel. We assume that the fluid is Newtonian. And we also assume that it's a liquid, so it's incompressible. All right, so if we start from first principles, we want an equation that describes the flow of fluid through the channel. There's a conservation of mass, and then there's the conservation of momentum. The conservation of momentum is sometimes referred to as the Navier-Stokes equations. Sometimes they're both together referred to as the Navier-Stokes equations. But basically, it's a statement of conservation of mass. This is what's called the material derivative. It's set equal to 0. And then you have the, I'm sorry, this is the material derivative. This is just the divergence of the velocity. That's equal to 0, basically saying that mass can neither be created nor destroyed at any point. The conservation of momentum. So there's different parts of this equation which cancel out, as it turns out, in microfluidic devices. And this is one of the reasons why microfluidics devices can be used in diagnostics quite well, because the flow patterns are so predictable that they can be reproduced in various devices. So let's look at some of the simplifications that happens. First, defining things. The velocity is the velocity vector is u, and that's in bold. Okay, so that's the velocity in the x direction plus the velocity in the y direction plus the velocity in the z direction. It's a vector quantity. Then there's the pressure, P. The viscosity is the material property, that's U. The density of the fluid is rho. Don't confuse P and rho. And wherever you have this del squared U, so that's the Laplacian of the velocity vector. Ux, Uy, Uz. So these are all partial differential equations. We generally don't like to solve them by hand if possible. We use a simulator to solve them, and in fact in this class you're going to be using COMSOL to solve the flow in some types of microfluidic channels. To solve a partial differential equation like this, you need to have a set of boundary conditions. I mean, one of the boundary conditions we've already talked about. The most common one is the fact that you have a no-slip boundary condition at the walls. The velocity at the walls is equal to 0. So you can say Ux, Uy, and Uz wherever you're at the wall. Whenever you're at the walls, it's equal to 0. That's an example of a boundary condition. But let's see if it's possible to simplify some of these things. So this term here, this is a material derivative term. This actually results in nonlinear terms in the Navier-Stokes equations because you have this U multiplied by the gradient of U here. That will result in nonlinear terms. And the nice thing is that at low Reynolds number, okay, when remember Reynolds number is the ratio. Does anyone remember what Reynolds number is? The ratio of what force to what force? Inertial to viscous force. That's correct. So this term in the equation actually represents the inertia of the fluid. Okay, remember, think about fluid packets flying through a channel, right? That fluid packet could have some momentum associated with it, right? Because it has mass. So the way that you know it's a momentum term is because it has this density in there. Density is represented by mass. So this momentum, the force resulting from momentum, that disappears at low Reynolds number when viscous forces become more significant. Now, this term here is the viscous force component. This term here is the inertial component. Okay, so when you're at low Reynolds number, this term becomes insignificant. And that turns out makes the Navier-Stokes equations much, much easier to solve and much easier to work with to the point where you have analytical solutions to it. Okay, plug and chug type things. So this one goes away at low Reynolds number. This term here, this is the force due to gravity. Any packet of fluid is going to be exposed, you know, as long as you're doing experiments on Earth, you have this gravity term here. But in microfluidic devices where you're at low bond number, this term goes away. Now bond number has to do with the gravitational forces versus surface tension, but there are dimensionless numbers that describe the gravitational forces versus viscosity and inertial forces and so on. But the basic thing is that when you're at small devices, gravitational forces are less significant. Surface tension forces are significant. So we'll have to leave that one in there for now. But if you're dealing with single-phase flow, you can get rid of this term. Okay? If you're dealing with multi-phase microfluidics, where you're dealing with the flow of droplets, air bubbles, or water bubbles through a channel, then you cannot ignore this term. You have to consider that one. So by ignoring these three terms for the time being, we can simplify the equation to this. So we only have three terms here. Now, this term here, if we're looking at steady state flow, steady state means like we're not transient changes in flow, but steady state flow, this term will also go away, and you're just left with just this equation here. Okay? So from this quite a complex partial differential equation, by taking some simplifying assumptions, which occurs at the microscale, in single phase flow, you come up with the steady state Stokes flow equation. The gradient of the pressure is equal to viscosity times del squared of the velocities. This is a this has to do with the viscous forces. The viscous forces on the shear stresses on the fluid element. This has to do with the normal forces, the pressure exerted on the fluid element. So this type of equation is easy to solve in various types of flow conditions. Okay, so these are all examples of low Reynolds number flow. And these examples are from Professor Brian Kirby's online lectures and also his textbook, Micro and Nanoscale Fluid Mechanics. if you're interested in the hardcore, the fluid mechanics of microfluidic devices, this textbook is very good at addressing that. And he also has some very nice online lectures on YouTube. So check that out if you're interested. There's a couple types of flows which fluids engineers talk about just as some very canonical and basic types of flow. One type of flow is called Couette flow. This is where you have moving plates. So if you take if you have a thin fluid layer and you have two plates on either side of it, and you move one of the plates, the fluid is going to move with the plate, right? So we talked about no-slip boundary conditions. If your wall is fixed, if your wall is not moving, the fluid flow velocity at the wall is going to be 0, right? But if the wall is moving, then the velocity of the fluid is going to be whatever the velocity of the wall is. Okay, basically, no-slip means that the fluid moves with the wall. If the wall is not moving, the fluid is not moving. If the wall is moving, then the fluid is moving at the velocity of the wall. So let's say you have two moving plates. One is moving at a faster velocity than the other one. Then you're going to set up a nice linear velocity gradient across there. Couette flow might happen if you have, let's say you're using a liquid, an oil as a lubricant in an engine, and so you have these moving parts and there's an oil layer between them. So that's one example of where this type of flow may happen. So this turns out this type of thing, it's a nice orderly, it gives you a nice orderly equations, the Navier Stokes equations. There's no pressure here, so this pressure term is 0, and you're just left with viscosity times d squared u dy squared. There's just a velocity gradient in one direction, and this so you get a nice solution to the Navier Stokes equations. This is an equation for the velocity ux, the velocity in the x direction. Okay, you can see that this is a linear equation which depends on y. Okay, so the smallest velocity is here, the largest velocity is here, and there's just a linear variation in between them. That's what's described by this equation. And the shear stress, the velocity gradient is a constant, right? The derivative of a line, the derivative of 2x is equal to 2, right? The derivative of a line is a constant. So the du dy, the velocity gradient, is a constant here. The velocity gradient is constant, and the shear stress is also a constant. So you have a constant shear stress given by this formula here. So the type of flow that we would get in a capillary, a tube, that's called Poisseuille flow. So this is more, closer to what we see in microfluidic channels. Now the classic version of Poisseuille flow is described as a circular cross section, so a circular pipe. So it's an axisymmetric solution. It's symmetric about as you go around the circle. It's symmetric. So the solution to the Navier-Stokes equation is a function of r. The radius, again, I mentioned that it's axisymmetric. It's not a function of the polar coordinate, theta. It's just a function of the radius. Now, think about the flow through a pipe. The walls of the pipe are not moving. Okay? So the velocity at the walls of the pipe are 0. The fluid velocity here is 0. The fluid velocity here is 0. The velocity reaches a maximum in the center of the pipe. Okay, it turns out that the profile is parabolic. Poisseuille flow describes a parabolic flow profile. This is the type of profile that you'd get if you're flowing fluid through a circular capillary. All right, it's described by this equation here. Delta P is the difference in pressure between one side of the pipe and the other side of the pipe. The more the pressure difference, the higher the flow velocity. And you can also see that it's a parabolic function of the radius. Okay. When r is equal to 0, you'll reach a maximum flow velocity. When r is equal to big R at the walls, the velocity will be equal to 0. The average velocity in the pipe. Okay, so if you were to take this flow profile and find the average velocity over the cross-section of the pipe, just by integration, you'll find that the average velocity looks something like this. The shear stress is given by R divided by 2 delta P over L. There's an important intuition here that you should understand. At the walls, the velocity is 0, but the shear stress is at a maximum. I'll say that again. At the walls, the velocity is 0, but the shear stress is at a maximum. That's where you have the maximum velocity gradient, the maximum slope in this velocity profile, so you have the maximum shear stress. Now, what do you think the shear stress is going to be here, right in the middle? What's the slope of this? What's that? Not infinity. Actually, the opposite. It's 0. Yeah, the slope du dy at the center is 0. So the shear stress in the middle of the pipe is actually 0. So at the middle of the pipe, the velocity is at a maximum. The shear stress is at minimum. Is at 0, actually. Okay, and you can see that by this equation here. Now, if we take the ratio of flow rate to pressure gradient, then we can find the hydraulic resistance. First of all, the flow rate is the velocity, the average velocity times the cross-sectional area of the pipe. So this is the relationship for the flow rate. Now, if you take Q divided by delta P, similar to V over I that we talked about in Module 1, if we treat this pipe as an electrical, as a resistor, the analogy was that pressure is analogous to voltage, and flow rate is analogous to current. So if we want to make an electrical circuit modeling this thing, the hydraulic resistance would be the ratio of flow rate divided by pressure, V over I. That's the resistance. So the hydraulic resistance for a circular pipe is given by Q divided by delta P, and that's just given right here. 8 mu L divided by pi R to the 4th. Notice we have R to the 4th here. Okay, the radius, the hydraulic resistance really does depend on the radius of the pipe. It's the radius to the 4th power. So in microchannels, we get large hydraulic resistances. All right, so you have to have relatively significant pressures driving flow through a microfluidic channel. We will leave this here. Next time, in next class, we'll talk about flow in a rectangular microchannel. So we talked about the circular pipe here, but in most cases, microchannels are rectangular in nature. So we'll start talking about flow in a rectangular microchannel and channels with other cross sections. And then we'll start talking about laminar flow, diffusion, and how fluids behave, or how fluids mix and diffuse together inside microfluidic channels, and some of the different applications of that. So we'll get into gradient generators and mixers and things like that. Okay, so let's end here today.